In this work, photopyrolytic technique is used for thermal diffusivity measurements of colloidal suspensions of silica at different concentrations. On the first place, let me give you a brief explanation about this technique. Photopyrolytic spectroscopy is based in photothermal phenomena. These are physical phenomena which takes place due to heat generation after absorption of modulated radiation. There are a lot of applications of photothermal techniques. They can be used, for instance, for thermal and optical characterizations, for qualitative and quantitative analysis, and medical applications, among others. The qualitative description of these techniques involves the heat diffusion problem across various layers, 2 layers in this case. In this model, S and W media absorb radiation according to the Birch-Lambert model with optical absorption coefficients beta sub S and beta sub W. The set of differential heat diffusion equations must be complemented with the usual condition of heat flux and temperature continuity across the interfaces and the limiting conditions on vanishing temperature as X goes to plus and minus infinity. The analytical solution is very complicated, but if the optical absorption coefficient of the sample, beta sub S, is assumed at infinity, and considering other appropriate theoretical conditions, the mathematical expression reduces to a very simple exponential expression, which is shown here. H is a complex constant independent of the sample thickness. In this, the amplitude decays exponentially when the thickness increases, and this decay depends on the thermal diffusivity of the sample, as it is shown. Here is a cross-section of the experimental setup. The layer between sample and pyrolytic sensor is a protection material for this last. To ensure in the surface absorption model, a thin slab of a strong optical absorbing material, a thin silicon slab in this case, is set up between the light source and the liquid sample. This is a picture of the actual photopyrolytic setup in my lab. Diode laser at 660 nanometers was used as a light source. The Stuber method, with some modifications, was used for nanoparticle synthesis. Silicon nanoparticle size of 661 nanometers and 673 nanometers were obtained as a result. The pyrolytic amplitude in semi-log scale as a function of the sample thickness is shown here for silica colloidal suspension at a concentration of 3 milligrams over milliliter. The perfect straight line behavior is evident. The slope of the linear fit is used for thermal diffusivity calculations through the expression shown here. All measurements were done at a fixed modulation frequency of 1 Hz. The thermal diffusivity is obtained for all the colloids at the 2 different sizes and at a different concentration are shown in this slide. It's evident here just a small increment in thermal diffusivity of values as function of nanoparticle concentration. This contrasts with thermal diffusivity values reported in the literature, but obtained with photothermal techniques which involves optical properties of the sample. Colloid suspensions have strong scattering properties, Tyndall effect, which strongly influence thermal diffusivity calculations when using these last techniques.